Today, we are going to take apart a single Ansys Workbench project, one that couples an electromagnetic solver to a thermal solver, and understand it the way a design engineer has to understand it. Not just how to click through the setup, but what is physically happening at every stage of the exchange between the two physics. This project links Ansys Maxwell 3D, running an eddy-current solution at 40 kHz, to a transient thermal analysis solved in Mechanical APDL. It was built to reproduce a very concrete physical object, a hand-wound induction heating coil energizing a cast iron rod. And unusually, for a teaching example, we have real bench measurements to hold it against. A simulated peak of about 301 degrees Celsius, compared with a measured maximum of 368.5 degrees on the actual rod. That gap is not a footnote. It is the most important lesson in this entire presentation, and we will spend real time on it. What you are looking at is not a diagram I have drawn for illustration. It is a direct screenshot of the live Workbench project tree. I want you to get comfortable reading this because this schematic is the entire architecture of the simulation in one picture. On the left, System A, is the Maxwell 3D design, its geometry, its electromagnetic setup, its solution, and a set of parameters it exposes to the rest of the project. On the right, System C, is the Transient Thermal system. Engineering data, a shared geometry, the mesh, the thermal setup, the solution, and the results. Sitting between them, System B, is a component called the Feedback Iterator. Notice the magenta lines. Those are not decorative. They are live data links. They carry the Maxwell solution and its parameters into the Feedback Iterator, and from there into the thermal setup. And at the bottom, both systems drop their parameters into a single shared parameter set. That shared bar is what lets us track quantities, like the ohmic loss and the maximum temperature side by side from a single project, across as many design points as we want to run. Everything else in this presentation is really just an explanation of what flows through those magenta lines and when. Before we go further into the mechanics of the coupling, I want to be very precise about what each solver is actually responsible for, because confusing the two is the single most common conceptual error I see in multiphysics work. Maxwell 3D on the left is an eddy-current solver. It answers exactly one kind of question. Given this current and this frequency, where in space is heat being generated, and how much? It does this by solving Maxwell's equations in the frequency domain, at a single frequency. In our case, 40 kHz. Its output is a spatial map of time-averaged ohmic and hysteresis loss density. What it does not do is model heat diffusion, and it does not track time in seconds. There is no later in an eddy-current solution. There is only the steady-state field pattern at one frequency. Transient thermal, on the right, answers the complementary question. Given this heat source, how does temperature evolve over real, physical time? It solves the transient heat conduction equation, stepped second by second, using Maxwell's loss map as a volumetric heat source, and applying convection and radiation boundary conditions together with temperature-dependent conductivity and specific heat. Neither of these solvers on its own can answer the other one's question. That is precisely why we need a coupling between them. And that coupling is what the rest of this talk is about. Let's now open up that coupling and look at exactly how a number computed inside Maxwell ends up as a heat load inside a thermal solver, because this is where most students' intuition quietly breaks down. Step 1. Maxwell solves the eddy-current problem on its own mesh, and for every single tetrahedron in that mesh, it computes a volumetric ohmic loss density, watts per cubic meter, at every point in the coil and the rod. Step 2. That field is not simply written out as a number. It is exposed through an internal object called an Ansys heat loss data object. Think of it as a heat loss provider. that carries the full spatial distribution, not a single scalar. Step 3. The transient thermal setup consumes that object, together with its own mesh from the model cell, and maps the loss volumetrically onto that thermal mesh, which in general is not the same mesh Maxwell used. This mapping step matters enormously in practice because a coarse thermal mesh can smear out a very localized electromagnetic hotspot. Step 4. Mechanical APDL then treats that mapped field as a distributed body heat generation load applied to the shared solid bodies for the full duration of the transient run. The point I want you to take away is this. This transfer moves a field, not a scalar. Every element gets its own local value. That is exactly why the coil's turns and the skin layer near the rod's surface heat up differently from the core of the rod. The physics of where the loss actually sits is preserved all the way through the coupling. Now, there are two fundamentally different ways to couple an electromagnetic solve to a thermal solve, and this project deliberately uses the more sophisticated of the two. The simplest workflow is one-way coupling. Maxwell solves once, using material properties evaluated at room temperature. That loss map is imported into Transient Thermal exactly one time, and the thermal solver then runs its entire time history against that fixed, unchanging source. This is fast, and for many problems it is perfectly adequate. But it is quietly wrong whenever the electrical conductivity, sigma, or the magnetic permeability, mu, change significantly as the part heats up. And in an induction heating problem, taking a rod from room temperature toward 300 degrees or more, they absolutely do change. This project instead uses two-way coupling through the feedback iterator we saw in the schematic. Concretely, the iterator is wired to the Maxwell solution and to both the setup and solution of the thermal system. After each thermal exchange, the current temperature field is written back into Maxwell. Maxwell then re-evaluates its temperature-dependent sigma and mu at that new temperature and resolves the electromagnetic problem. The updated loss map is re-imported into the thermal solver, and the cycle repeats until it converges or reaches an iteration limit. This is a genuinely more physically honest simulation, and, as we will see in a few slides, it is still not the whole story when we compare it against the bench. This slide is, in my view, the single most important conceptual slide in the whole deck, so I am going to slow down here. Look at the 4 lanes. Maxwell, at the top, only ever solves in the frequency domain. It has no internal concept of seconds. The loss map, the second lane, is therefore a step function in time. It holds one constant value for an entire iteration and then jumps instantaneously at the moment of a feedback exchange. It does not drift smoothly. Now, look at the third lane, temperature. This is the only one of the 4 quantities that evolves continuously, in real physical seconds, because it is Mechanical APDL's own internal transient integrator that is advancing it, using whatever loss value currently happens to be loaded. And the fourth lane, sigma of T and K of T, the temperature-dependent material properties, updates in lockstep with the loss map, not continuously. They are refreshed only at the moment Maxwell is resolved. So if a student asks me, does the model account for the resistivity of the rod changing continuously as it heats? The honest answer is, not continuously, only at each feedback exchange whose frequency is a setting the analyst chooses. That is a real modeling approximation, and it is one of the reasons, as we will discuss later, that a two-way coupled simulation can still disagree with a bench measurement. Let's now put a precise equation to what Maxwell is actually computing. The ohmic loss density at any point is the magnitude of the induced current density squared, divided by the electrical conductivity at that point's local temperature. P equals J, squared over sigma of T. This is evaluated once per Maxwell solve, at the drive frequency, which for this project is assumed to be 40 kHz. Three things are worth dwelling on. First, what Maxwell is really solving is a single frequency domain problem, so its output is a cycle average loss density. For all practical purposes, instantaneous compared to the much slower thermal timescale over which the rod actually heats. Second, this loss can still evolve over the course of the simulation because sigma of T depends on local temperature. As the rod heats, its resistivity rises, which changes both the magnitude of the loss and, through the skin depth, its spatial distribution. But, and this is the same point from the previous slide, that change is only captured when the feedback iterator triggers a resolve, not automatically at every thermal time step. The contour on the right shows the actual result from this project, a maximum ohmic loss density of about 5.7 times 10 to the 7th watts per cubic meter, concentrated near the surface, falling to under 10 watts per cubic meter deeper in, and near zero toward the base of the rod. A beautifully clear picture of the skin effect in action. I want to draw a sharp distinction here, because these two conductivities are both called conductivity. They both depend on temperature, and yet they do almost completely different jobs in this simulation. Electrical conductivity, sigma of T, lives inside Maxwell's material assignment. It has nothing to do with the engineering data branch of the thermal system. It governs how strongly eddy currents form and how deeply they penetrate, because skin depth is proportional to 1 over the square root of sigma. For the rod material assumed here, cast iron, resistivity increases with temperature, so sigma falls as the rod heats. And critically, this property is only reevaluated at a Maxwell resolve. It does not update on the thermal solver's clock. Thermal conductivity, K of T, is a completely different animal. It is defined in engineering data as a temperature-dependent curve. This project actually stores two separate such data sets. And it governs how quickly heat generated near the surface diffuses inward toward the rod's core. Unlike sigma, K of T is read continuously by Mechanical APDL at every single thermal time step, with no waiting for a feedback exchange. This is the property that directly shapes the temperature gradient along the rod that we will compare later against the actual surface reading from the infrared thermometer. The governing equation on this slide is the transient heat conduction equation. Rho show the density times Cp, the specific heat times the partial derivative of temperature with respect to time, equals the divergence of K times the gradient of temperature plus our volumetric source term, P of xyz. Mechanical APDL solves this at every internal time step of the transient run. Four things feed into that solution. The heat source term is simply the last loss map imported from Maxwell, held fixed between feedback exchanges. The material response, Rho, Cp, and K of T, determines how quickly a given amount of loss turns into a local temperature rise, and how far that heat spreads before the next exchange. The boundary conditions capture convection to the surrounding air, and, importantly, radiation, which becomes very significant once the rod is genuinely glowing, as ours is. And the time stepping itself is handled by APDL's own Transient Integrator, which subdivides the run into internal substeps for numerical stability. Substeps that are typically far finer than and completely independent of the feedback exchange interval. The headline result from this project: a maximum temperature of approximately 301 degrees Celsius and a minimum of about 259 degrees along the rod at the final time step. Let's look at that result in full on the next slide. Here is the complete transient result, shown as two snapshots of the same rod. At time 0 on the left, The entire rod sits at a uniform, cold starting temperature. You can see the color contour is flat. By the end of the simulated run, on the right, a clear thermal gradient has developed. Hot at the top, where the coil couples most strongly, cooling steadily toward 259 degrees near the base. This is exactly the kind of result a single static contour plot can hide. Watching the sweep from cold to roughly 301 degrees makes it obvious that the heating is not uniform along the rod's length. It is concentrated where the coil's magnetic field actually links with the part, which is precisely what our discussion of coupling and skin depth predicted it should be. Let's step back from the physics for a moment and look at the actual CAD model behind these results. Because a simulation is only as trustworthy as its correspondence to the real part. The geometry is a helix coil, built parametrically from measurements taken directly off the physical coil. 18 millimeters inner diameter, 22 millimeters outer diameter, 2 millimeter wire, 10.5 turns, wound around a solid rod whose material we are assuming to be cast iron. I want to be honest about that word assuming. We did not run an independent material assay on this specific bar, and that assumption turns out to matter later. The excitation is a solid current source of 10 amps at an adaptive frequency of 40 kHz, chosen to match the ZVS driver's real resonant operating point. And the solver is the eddy-current solver, which, as we established earlier, produces exactly two things: the electromagnetic field solution and the ohmic loss map that feeds everything downstream in the thermal coupling. Everything up to this point has lived inside Ansys. This slide is where the model has to answer to reality. Here is the actual benchtop rig, a 120-watt ZVS induction heating driver, powered from a 12-volt, 20-amp switching supply, driving a coil that we wound by hand around the same rod geometry, modeled in Maxwell. This is not a rendering. Every part you see here is the physical hardware that produced the glowing rod, the coil, and the thermometer reading we are about to look at. If our simulation is going to mean anything as an engineering tool, it has to be checked against exactly this kind of physical evidence, not just against itself. This single photograph carries more weight than almost anything else in this presentation, so let's read it carefully. This is the on-screen display of the infrared thermometer used to measure the rod during heating, and it is logging a maximum temperature of 368.5 degrees Celsius. Three details on that display matter for how we interpret the number. First, the max hold reading, 368.5 degrees, is the peak the instrument captured during the observation window, not a single instantaneous spot reading, which makes it a fair quantity to compare against our simulation's peak temperature. Second, the emissivity setting is fixed at 0.95. That number is not free. It is an assumption baked into every reading this instrument produces, and if the rod's actual surface emissivity differs from 0.95, especially once it is oxidized or glowing, the true temperature could differ from what is displayed. Third, this is log entry number 51, which tells us this measurement was taken as part of a deliberate logging sequence, not a one-off snapshot. Keep this number in your head, 368.5 degrees. We are about to compare it directly against the simulation. I like this slide because it puts three completely different representations of one physical event side by side and asks you to hold them in your mind simultaneously. On the left, the thermal simulation's temperature contour, the consequence, the thing we ultimately care about, peaking at 301 degrees. In the middle, the real rod itself, glowing visibly red-hot on the bench mid-heating, the ground truth we are trying to predict. And on the right, the eddy-current source, the ohmic loss density map, which is the electromagnetic cause underlying everything else on this slide. Read left to right and the logic runs backward from effect to cause. The glowing rod in the middle is what actually happened. The loss map on the right is why it happened. and the contour on the left is our computational attempt to predict it. Keeping all three in view at once is, frankly, the entire discipline of applied electromagnetics and thermal design in a single image. Now we arrive at the most important slide in this presentation. So let's take our time with it. On the left, the simulation, approximately 301 degrees Celsius. The peak rod temperature at the final time step, produced by our assumed 10 amp, 40 kHz excitation. On the right, the bench, approximately 368.5 degrees. The max log surface, reading from the infrared thermometer, at an assumed emissivity of 0.95. The gap is about 67.5 degrees Celsius, and notice which direction it runs. The bench measurement is hotter than the simulation. I want you to sit with that for a moment, because it is the opposite of the lazy assumption many students make, which is that a real system should always run cooler than an idealized simulation due to unmodeled losses. Here, the real rig is outperforming the model's prediction, which tells us, immediately, that the discrepancy is far more likely to be sitting in our input assumptions than in some missing loss mechanism. 4 candidate explanations. And I want you to notice that 3 of the 4 are about what we assumed, not about what we measured. First, excitation current uncertainty. We assumed 10 amps, but Ohmic loss scales with the square of current, so even a modest error in the real driver current gets amplified substantially in the resulting heat. Second, the frequency assumption. 40 kHz is the driver's nominal resonant point, not a frequency we independently measured on this specific run. Third, the rod material assumption. We modeled cast iron, but the real bar's actual resistivity and magnetic permeability may differ from handbook cast iron values, which shifts both the loss magnitude and the skin depth. And fourth, the measurement conditions themselves. An emissivity of 0.95 was fixed on the meter, and a partially oxidized or actively glowing metal surface can genuinely deviate from that assumed value. This is exactly the comparison loop that any serious validation exercise goes through. You do not simply average the discrepancy away. You use it to go back and tighten the specific inputs most likely to be wrong, and you rerun the model until simulation and bench genuinely agree. Let's convert everything we have discussed into a concrete, repeatable checklist you could hand to someone setting this project up themselves. In Maxwell's setup, solver type eddy current, excitation solid at 10 amps, adaptive frequency 40 kHz. In engineering data, assign temperature-dependent K of T, along with specific heat and density for both the coil and the rod materials. In Maxwell's solution, confirm that ohmic loss and core loss, if relevant, are actually available for export before you build the coupling. On the Feedback Iterator, set your exchange interval and your convergence tolerance for the sigma of T-driven resolves. This single setting controls how often the step function we discussed earlier actually updates. In Transient Thermal setup, drag Maxwell's solution cell onto Thermal's setup cell to create the heat loss link. In Thermal's analysis settings, control your initial, minimum, and maximum substep sizes, your end time, and your ambient and convection boundary conditions. For bench validation, log your clamp meter current and your infrared max surface temperature at the same elapsed time as your simulation's endpoint, not at some arbitrary later moment. And finally, and I would argue most importantly given what we just saw, treat your driver current, your operating frequency, and your rod alloy as things to verify directly, not things to assume. Let me leave you with 6 things worth remembering long after the details of this specific project have faded. 1. The link between Maxwell and transient thermal is a field, not a number, a full 3-dimensional volumetric loss map, mapped mesh to mesh. 2. That loss is a step function in time, constant between feedback iterator exchanges, with temperature as the only quantity that genuinely evolves continuously. 3. Sigma of T and K of T Update on entirely different clocks. Sigma only at a Maxwell resolve. K at every single thermal substep. 4. The model was deliberately built to match a real physical coil. The same 18 by 22 mm, 2 mm wire, 10.5 turn geometry we measured on the actual bench part. 5. Several of our key inputs, 10 amps, 40 kHz, cast iron rod material, are modeling assumptions, not independently verified facts. And that distinction matters enormously when you interpret any result. And 6. The finding I want you to remember above all the others. The simulation and the bench do not agree yet. Approximately 301 degrees against approximately 368.5. And that disagreement is not a failure of the exercise. It is the exercise. A validation gap you can explain and can act on is worth infinitely more than a simulation that was never checked against reality at all. That concludes our walkthrough of the workflow, the coupling, and the bench-validated results. Thank you.